Thank you, everybody, for coming. It's first meetup and hopefully a series of meetups we're going to have on the topic as we go forward. And so I'm Serge Mankovski, one of the organizers. Maria Velis Rojas is an organizer of Meetup. And Maria will be running the show today. She will be announcing speakers and introducing.
Oh, sure. Thank you again. This is really exciting for us to have you here. We were very excited about how much interest there was in the Bay Area on this topic. We hope to make of this meetup a place to start discussion about the different topics related to big data. And you will see today some diversity in the topic as well. We are considering big data from the point of view of human-computer interaction. We think about the different products that are available in the market, as well as different tools for implementing prototypes. And we are trying to bring people from organizations as well from academia and government organizations in the Bay Area to talk to you. We are looking for topics, so feel free to let us know what do you want us to find, what kind of speakers. If you think somebody should be here and you want to recommend that person, feel free to send us an email or a message in our website. And we think that there will be more people coming later. We just have a few messages from people coming that there's a big traffic jam on 101 due to an accident. So actually our third speaker is still in the traffic jam on the way. Hopefully he will be able to make it. He will be the last person to talk today. We have three really good talks today. The first one to talk will be Serge. Serge Mankovski is an expert in IT. He has been involved in the area of IT management for more than 30 years. He is a researcher here at CA. And he will talk about some of the general aspects of how are we approaching the big data problem here in CA. So you will see a little bit of combination on design of visualizations, our use cases in the concept in the area of IT, as well as some technical approach. And once we go to the second meeting, I will give you a little bit more information about our speakers. We have two talks, one after the other, 30 minutes each. Then we have a small break, and we'll have our last talk. So I hope that you enjoy this, and Sergey, you can go ahead.
All right. So I'll be talking about visualization and IT management. So CA, you probably know CA by the name of Computer Associates, and CA Technologies. Now we're called CA Technologies officially. So the company has been around for almost 30 years, and it has always been focusing on managing very large IT environments. We're talking about major companies in the world. Pretty much any company that does business, like large business in the US, is probably our customer. It's very likely. So we deal with really, really large IT environments that have a lot of elements to them and a lot of detail. So we kind of approach this problem of big data before it was even called big data, because we were facing very diverse and very fast-changing environments. But once the term was coined, then we kind of started to think about our problem as really a big data problem, and we kind of realized the visualization techniques that we'd be using, we're having problems with. They're not really working in the environments we have, velocity, variety, and volume of data that we're actually dealing with. So it's not only that, it's now, as big data idea is starting to take root, people are getting more appetite for actually mashing up that data and using different data from different sources, but actually adds to the complexity of the data itself, right? It adds to the variety of things that you want to actually fit on your screen with visualization, but you have only so much real estate on it. And then also we want to look at the data in a longer time frame. So all that compounded really brings us to the point that we wanted to look into this problem of managing visualization of what people are looking for in the context of IT use cases in a different way. So we kind of started to, in our domain, we really need to find new solutions. So this is our problem. So this problem is really a lot of the data that we are working at can be actually summarized as a graph. And these graphs become extremely large. So essentially, if you look at one mainframe LPAR. LPAR is really a virtual machine in the mainframe environment. You can have up to 30,000 items that you want to track in that environment. And the way how you track them is essentially these little diagrams where you have one element connected to another element, and they're connected through links like hosts or FTPs to or sends data to and things like that. And what you do with these graphs, you do things like root cause analysis. So if something happens here, what you really want to do, you want to go back in this graph and see what happens here because that influences it. And also you want to do things like impact analysis, the reversed problem. What would happen if I change this thing? Because it impacts all those things. How would they be impacted and how that would actually go through the graph down? And you can actually have very, very deep graphs, and the impact can be very deep. This is a visualization of a really simple picture, simple element of that visualization, and it's completely zoomed out, and you cannot even see the edges of it. So how do you really deal with this problem so that you could start recognizing things for what they are? Because among these elements, there are services, there are networks, there are locations, there are different things engaged into different relationships with each other, but you cannot really have a handle on it. So this is what we are dealing with. We realize that this problem is not really unique because if you look at the diagram, that's Facebook famous picture, right? Very large graph, great. Problem is, it's mesmerizing, but it doesn't tell you anything. You cannot really get anything out of it, except what you already know. So those talk to, okay, great, continents talk, and there is more density of people using in the US, the East Coast, West Coast. Well, we kind of know that.
Point on the laptop so that we can see it here.
All right. Well, it's kind of awkward.
Okay.
Anyway, okay, I'll try to do it. So, and that is common because what you see on the right here, it's a GIF visualization of Voltaire network, you know, and this is GraphViz, and this is one of the commercial products that people probably would recognize, but it's actually the same problem. It's hard to see from a big picture what is really in the detail, and you have to zoom into detail, you lose a big picture. So this is what the dilemma is. We want to have access to detail. At the same time, we want to reduce screen complexity. We want to be able to somehow or other get to the point of what we are looking for without actually doing anything external to what we are trying to accomplish. If you want to do root cause analysis, we really want to understand things that are related to each other, but the systems don't know about it. We have to somehow or other tell them about it. So how we approach that problem is really kind of breaking the paradigm in a way, because usually what people do, people try to put as much as possible with some tricks and interesting colors combination or whatever that draw your attention to important things, use various layouts to highlight different aspects of data, and use overview and zooming. So we kind of been there, done that. We've done it for many years. So we decided to kind of change that approach, given even the limitations of mobile devices or browsers. For example, if you were to create a large visualization in the browser, you're stuck with the problem of actually limitations of a browser. So the browser can only show so many objects on the canvas. And you really want to really reduce that amount. If you go on a small screen, you really want to be very concise. So we want to use simple layout, and we want to show some sort of level of semantic zooming. Semantic zooming is similar to what, let's say, Google Maps does. When you go on different levels, you shoot different types of things. You don't see, that the amount of detail at the highest zoom level. So they kind of have that for the terrain, which is kind of a normal and for us understandable metaphor. We understand the language of terrain, but how does it look like in the enterprise environment? So how would a map look in our environment? This is what they came up with. So we decided to look at the entire enterprise terrain is your asset. So everything you own in enterprise, all the servers, all items that you track, that you consider to be important, this is your terrain. And over that terrain, we superimpose kind of things that combine those elements of a terrain into something that you care about. Let's say we can have a layer that keeps all the servers in the layer, and we can have another layer that keeps all the systems or applications in the layer, and then they can somehow interact. So if services use applications, then we can show that interaction between the services, the inclusion, the fact that service 5 here is using application 6 is shown by clicking and highlighting those elements at the same time. So not directly linked, but they're linked by highlighting. So the way how we form these layers, we essentially go and look at the models, which are usually trees, not even graphs, they're usually trees. And then we project those trees on surfaces. And so what we do, let's say this is a typical application. So this is, let's say, a service that consists of applications, and they work on systems and they use networks, and every layer would represent a different type of element in your environment. And you can think about graphs that you work on and think what they can represent, because it doesn't matter. You can assign, this is why it's color-coded, it's not even labeled here. So what now we'll be doing, we'll be assigning blue elements to the blue layer. So now we're in the blue layer and those services are there, and then we can go and do that whole thing for all the layers that we care about. So we can define, let's say we want to have a services layer, we can have applications layers and systems, networks, and assets. So all of a sudden, your network does not look, your graph does not look a graph anymore. It looks like a stack of layers where elements of different types are sitting in those layers as elements of a set with set semantics. So now, next thing what you do, you look at the relationship between them, and you see that, for example, here, these blue elements, they share one green element underneath. So how you represent that in a representation, you really draw that relationship as an overlapping Euler diagram. This is not the best of the way to do it. There are better ways to do it, but just for the sake of clarity, we will show this. And so essentially what this Euler diagram shows you, that there is an element where all of these layers on top, all the elements from the top layer in your graph are interacting with at the bottom. So you do it across all layers, and you end up with this. So essentially for every layer, you have the same kind of visualization and diagram. And in that stack, what you can do, you can now start clicking on these things and selecting related elements. So now what happens, once you start selecting related elements, you can select and unselect these elements as you go along. What you're really doing in this process, you're actually understanding how things relate to each other, because in this stack here, what you described to you, the use cases of root cause analysis and impact analysis are implicitly present through these layers, because applications impact services. And services, as if something happens in the service, very likely that application was a cause of it, or something below, the network was a cause of it. And this is why you can actually browse this as simultaneous root cause and impact analysis diagram. So now what happens? This is where the trick really is. So now you selected these things, and they kind of, you unselect them at the bottom level, very fine details. You can actually unselect certain assets from the grid view here on the bottom. And what you're really creating is this. You're creating logical expressions. You're creating filters. Because we are using set semantics, you essentially have set semantics in the visualization. So you can have, so if you selected service 5, essentially you're saying, I want to get everything that service 5 is using. Here, if I select intersection, I just want to get, only those that belong to all these three services at the same time. And I can unselect and express not, and therefore I can actually do a logical expression. I can transport into the SQL query. And what I can do then, I essentially can go from that graph, going through this thing and saying, I'm really interested in these things, click, 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 and go to this. So the trick really is you don't change your visualization. You superimpose this kind of navigation mechanism and semantic selection onto your visualization and create a visual filter. So this way, you don't really need to remember any names. You still stay in the context of your use case. And you actually, by the end of the day, you get to the detail you need because you're really looking for this diagram, not that, right? So that's the trick. So now, it would be simplistic if we were not able to traverse multiple layers, because if you have two layers interacting, it's somewhat obvious, right? But where the problems usually are is a bit further removed. So for example, if a server runs on a rack, and the rack runs an application server, and the application server has a container has something else, it is not obvious from the get-go that the power supply on the rack has direct impact on the on application running in your system. If somebody went and changed something on the power supply, or you know, didn't change a breaker, didn't flip the breaker, you got a problem. But in your graph view, you don't see it because it's so far removed and so many steps away. So how do we actually deal with that problem? And we deal with it through semantics of those labeled relationships that we have. So all the elements have names, and names have attributes. So we can have actually a description logic description, like in terms of RDF or OWL, as you do it for semantic web. And you can reason about things like equivalency. So I'll show you how it's done. So we assign elements to the layers. We define layers. So here we have different colors, and different lines color different lines. The color of the lines represent different types of relationships. So once you've done that, you have red relationship, you have blue relationship, yellow relationship. And let's say you might reason through your description logic and say, well, yellow relationship is really the same as green relationship. And example would be, for example, relationship runs. So if something runs on a server, or something is hosted on a server, they're very semantically similar, except one thing. Runs really means it runs a software. Hosted, it means can be a data sitting on a system. But from point of view of failure, it doesn't matter. If there is no power to that box, hosts or runs doesn't matter. So we can actually collapse those two, and we can put this relationship in the layer in such a way that we treat them equal. The same way we can treat different classes equally. We can reason about equality and things. For example, a classic question, I worked in telecom years ago, and the question was, is a fax machine a printer? It is a printer, it prints. So if your printer doesn't work, you can fax the stuff you want to print to the printer. But multimedia systems did not know that. We wanted them to know that, but so we had to teach them. So here we can actually say printer is a fax machine is a printer, and a system can automatically infer that from description logic. So then you can essentially what you can do now, you can start putting different things in the layers. They don't have to be the same type of thing. As long as they're semantically equivalent, they can actually belong to the layers. And then the second trick is really transitive closure. So now the question is, well, if they're so far removed and something is in between, what do we do with that stuff? And the question is, the answer really is you can actually collapse that. It doesn't really matter. For transitive closure, as long as relationships are equivalent, you can traverse the transitive closure and put everything below it, regardless how deep it is. Let's say you said 20 layers deep, you can put it in a layer below, and then you can see the interaction between them. Questions? All right, so this is pretty much the whole trick, right? And we've done this with Euler diagrams, with different other types of visualizations, and they kind of work as long as you keep two things. You keep the set semantics, so your logical expressions work, and you have your RDF descriptions properly set up, so you can actually understand the semantics of elements, can reason about them. So and then you can put different visualizations depending on the domain. In our domain, this Euler diagram stuff works and kind of looks sexy. But in other domains, it might not, and maybe some other visualizations would be better. But what is important is that one of the points that I didn't really stress in the beginning, and how am I doing on time? I'm too fast, too slow?
44.
So what does it mean? I'm
15 minutes in.
15 minutes in. Oh, I'm almost done. Oh, I am fast. So I didn't mention before, so big data is okay, but we were talking about all that sort of stuff, but what did not change is that our time constraints on how fast the visualization has to be created. And one of the big things when you traverse really large graphs is that it just to collect the data for the graph visualization takes so long that you essentially hang forever there just to get the data. And you think it's visualization slow, but no, it's your back end. So what we've done here, to overcome that problem to some extent, we created a cache layer, a graph cache layer between our systems, our database systems, and the visualization. And the graph database in this environment essentially plays a role of a cache where all the important relationships are materialized in a graph view. And then we essentially use graph operations to produce our visualizations. And performance gains have been very, very interesting. And a lot of things that were needed for visualization can be much faster with the graph database operations rather than running joins on relational databases. So that is pretty much most of the stuff that I wanted to talk about, and I'm ready for questions. I just zoomed through the whole thing. And questions?
So in the previous graph,
Okay.
what are the other two? Yeah, so in the previous graph, yeah, apart from MySQL, what is OM and DX?
Oh, it's Oracle Enterprise. DEX is one of the visualization systems we used early on. It's in-memory graph database out of Barcelona. It's a company called Sparsity. We moved on since then we moved on to Neo4j. And what we are really interested in, and that's what we are doing right now, is there is a framework there called Blueprints. And Blueprints framework is really like JDBC driver to graph databases. Through Blueprints, you can actually write it once and run it on Titan. You can run it on InfiniGraph. You can run it on Neo4j, on DEX.
So, comparable to Neo4j, there is another graph database called GraphX.
We didn't try that one.
It is also from the Spark community.
Uh-huh.
And MPLab.
Yeah, we didn't try that. Well, what we are focusing on is on Blueprints compatible now, because that seems to be the way to go, because you write your code once. All these graph databases have different languages for traversing them. Some of them very fancy and very powerful, but what you really want, you want to have, ability to go from in-memory to, let's say, Titan big data. But Blueprints give you the ability to do that, right?
So you are meaning that if it is not able to do it in memory, then it goes into file system and does the processing work.
No, they're completely different environments. What Titan does, it's actually an overlay over Hadoop. It's using HDFS on the back end. So their graphs computed in a completely different way than Index. Index is essentially a sparse matrix in memory, right? And if it doesn't fit there, too bad, right? But in Titan, you don't have that limitation. The issue is with Blueprints is that if you write to the Blueprints interface, it doesn't matter. You can run on any of those systems. You run the query on them.
Do you use SVG at all, or only Canvas for web presentation?
We use right now HTML5. Maria using the HTML5 pretty much for.
Yeah, but there is like different types.
I think Maria is better. Can you? Yeah. Yeah.
So with the way you model the network, can you in real time show how a failure can cascade across the entire graph?
Well, it really depends. Like, for example, it depends on the graph. Right. Can we show how the failure ripples through the graph? Well, there are limitations on the back end. For example, some databases don't have transactional semantics. They wouldn't reveal, like for DEX, for example, couldn't even handle any update. It was just for exploration. Some of them would. Some of them would be doing that in eventual consistency mode. Some of them would be doing it in strong consistency mode. So it's really the question to the back end. To represent that failure is just a status change on the object. You can reflect the status change in the object in an update, sure, but whether or not database can actually do it in real time, it's another question.
But you should be able to use it for modeling failure.
Well, you see, this is a bit different. What you really want to do let's say, when you investigate a failure, right? You usually investigate a failure in the retrospect. You're not investigating it as it happens. As it happens, your question is, how do I plug this hole, right? What you're really interested in is a corrective action, right? So it's in retrospect, you can actually go and play it through and actually see what is happening. You don't really need to see the change of the status. What you really need to understand is why, right? It's your investigation. So this root cause analysis issue, really, what is at play, right? Because a lot of issues with propagating alarms is actually a big problem from other perspective. Think about it. If something happens on a power switch, everything goes off. Your router sending you messages or whatever, I don't ping that part of a subnet. Your application servers are screaming, I lost a peer. Your database servers, everything. But it's one problem. you really want to suppress that stuff. You don't really want to show that, right? So this is why it is, sometimes it is sexy and nice, but what you really want, you don't want to see that. You want to see one single event. And this is how you, in retrospect, can actually get to the single event. And hopefully, next time around, you'll suppress everything else. So what you want to show in that graph, root cause. Yes, that element is a culprit, right?
I guess where I'm headed. So where I'm headed with this is, can I use this kind of database and the querying system and the model to test the robustness of my architecture? So can I use this approach to say, well, if I configure things a little differently, then can I simulate failures?
Right, right. Well, you can simulate failures in the sense, so this is, yeah, going back. Yes, of course you can, but this is probably how you would want to do that. What you would want to do is this. So essentially you have your environment in which failure occurred. You don't know where the failure actually occurred. You also don't know where failure actually manifested, in what form. Some systems may manifest it as a symptom, some systems may manifest it as a root cause. You want to give that a label, create a layer, and see where that layer, over which elements those layers overlap. That might be a possible culprit, right? So what you really want to do, you want to do this kind of trick in investigation and in retrospect, right? So yes, you can, and that is actually the intent. You should be able to do all of those things, because it's not only important to understand the root cause, you want to prevent it later, so you really need to understand what was affected. Yeah. Any more questions? So question for you guys. Do you think this is about big data? Do you think that this something could be actually to get, that Facebook problem, friends of friends and, who are the friends of enemies things?
I think it's very difficult to map this on big data, because if you apply this to big data, like the data there is big as it is, right? So if you start putting the relationships and things, like just imagine, for example, that you're trying to understand the graph system in Facebook as an example, right?
Right.
That's a huge thing, right? Which has like at the minimum 600 million nodes.
Yeah.
Each of them with attributes and things and stuff, and then you put this on top of it. I mean, how is it going to work? So I think for a limited set of problems, it could be useful, right? But I think it can explode very fast to really large complexity, right? So
Right, and this is what we think about it as well. And Euler diagrams really don't hold up to that complexity sometimes. We're actually working on some other visualizations that don't have the problem. Euler diagrams are kind of tricky to lay out, and also put labels on it is pretty tricky, but something more regular than that, that's what we're looking for.
But the data is big, right? But the semantics graph is not big.
Well, it is still big. It can still be hundreds of thousands of millions of nodes with tens or maybe hundreds of different types of relationships, right?
And I didn't even get to the fact, like, for example, if you take if you use RDF for the storage, right? So then you want to extract subgraphs and then how you scale, even the infrastructure for that is difficult to scale. So you can crash under your own weight, kind of thing.
Well, yes, maybe. RDF reasoning might be a problem there, but again, there is still, I think, we didn't prove that, we don't have access to that data, right? But in our domain, types of relationships is probably about 3 dozen, something like that. Customers can come up with different versions of those, but they kind of boil down to the same set. And types of nodes, we have probably a variety, but it's not no more than probably several hundred different types of things. It's just a lot of instances of those things, right? So in a given data center, you have a whole bunch of versions of Linux router, yeah, they have components, maybe have a different types of components. It's still manageable amount of different categories. What is important, I think, and this is what I think this is what is missing in this whole big picture, is an aspect, kind of a silent thing of it. Do you know what do you have? Do you know what kind of distinctions you have in your data? Do you have your data catalog? Do you have the entire list so you can actually work with that list? right? So we kind of talk about big data and talk about big data storage and their schemas and no schemas and all this sort of stuff. But we kind of overlook this notion of a data catalog in the full sense of it. So Hive has that data catalog. It tells you, there is a schema and there is H catalog project and all this sort of stuff. But what about an EXIF file, EXIF data within the JPEG file, and within that EXIF a time format, right? It's not anywhere in the model. It has to be somewhere mentioned, right? We don't have that. Once we have that, then we can start counting how many different things we have, right? And we don't yet.
And one more point. We looked in the past for this kind of stuff, and I think there's some even theoretically hard problems with it. Like for example, you mentioned before the graphs look pretty, but they're kind of meaningless sometimes. Like in that example to the left top corner, right? So if you want to partition to extract some subgraph which has some kind of properties in there, as you probably know, that's an NP-hard problem, right? So partitioning your graph then becomes, so then how do you extract things from it? How do you do things with it, right? So it can become like, it's pretty again, looking at it, but reasoning about it and making sense of things, I think it's going to be very hard.
Right, in this sense, because it's actually an enumeration, it's not really partitioning of a graph, it's just filtering on enumeration. So we are not trying to split that graph according to some sort of a criteria, we just pull out elements, that's all. And kill the links if they are not there. Okay, all right, I guess it's 28 minutes. All right, I'll give 2 minutes back. So,
Great.
thank you.
Thank you so much, Serge.